This is what we are going to study. So it would be better if you take a pic of this and keep it beside while you are understanding molecular orbital theory. Let's understand molecular orbital theory, MOT, using hydrogen as our example. Now, what we have over here is atomic orbitals. So this is atomic orbital, this is atomic orbital, this is atomic orbital of hydrogen, this is atomic orbital of hydrogen, and this is molecular orbital of H2, dihydrogen. All right. Now, if we observe configuration of hydrogen, it is 1s1. So atomic orbital would have one electron in 1s orbital. Similarly, the other atomic orbital also would have 1s, one electron. Now these two orbital come together and form molecular orbitals. Molecular orbitals for bonding and for antibonding. Now, in case of S, it is frontal overlap. Two of the hydrogen S orbitals have frontal overlap, so it forms sigma bond. All right, sigma bonding 1s orbital and sigma antibonding 1s orbital. So these what I told were molecular orbitals. All right. Now it has two electrons, one of this atom, another of this atom. So these two electrons are to be filled in. Now these two electrons are to be filled in into these molecular orbitals. So as per energy level, this is at lower energy and this is at higher energy. I forgot to mention that this is called as barycenter. That is, as we say, center of gravity. This is the center of energy. The bonding orbital goes below the barycenter energy wise as much as the anti-bonding orbital goes energy wise above the barycenter. So energy lost here is equal to energy gain here. So energy wise, it's the theory of conservation of energy. All right. Now we have got two electrons to be filled in molecular orbital. One from this atom, one from this atom. These two electrons are filled in 1s, sigma 1s orbital, whereas sigma antibonding orbital remains untouched because there's no electron left to fill in. Two electrons are already filled into this. Let's try and understand bond order. Formula for bond order is number of electron present in bonding orbital minus number of electron present in antibonding orbital. All right, that is divided by 2. Now, when we talk in terms of molecular orbital of hydrogen, in hydrogen we know there are 2 electrons in the bonding orbital, whereas nil electrons in the antibonding orbital. So what we do here is, so bonding electron 2 minus antibonding electron 0 divided by 2. So it is 2 divided by 2, that is 1. What does bond order signify? It signifies number of bond present in between two atoms. So it is single bond. So hydrogen molecule possesses one covalent bond between two hydrogen atoms. Now let's understand magnetic behavior. Now magnetic behavior, there are two. That is, there are lots actually, paramagnetic, diamagnetic, ferromagnetic. But right now we are concerned with diamagnetic and paramagnetic materials. Now let's understand this. In paramagnetic, we have paramagnetic, parallel, and positive magnetic susceptibility. Paramagnetic is the property. For this property, when a material is paramagnetic, it aligns itself parallel to magnetic field and it has small positive magnetic susceptibility, which is represented by chi. Regarding susceptibility, I would be talking later on when I deal with magnetism. All right. And it concludes that it has got unpaired electron in its configuration. So paramagnetic, for paramagnetic, what I say is it is theory of 3 P's. Paramagnetic, parallel, positive, and the fourth one is not P. So it is unpaired electron. Alright, if it would have been paired, then it would have been all 4 P's. But just a way to keep it in mind. So it is theory of 3 P's. The fourth one is U, unpaired electron. So whenever there is an unpaired electron in the configuration, it shows paramagnetic behavior. And when we speak about paramagnetic behavior, it deals with all this. Alright, so what is diamagnetic? So here first one is obviously diamagnetic. Then it aligns, the material aligns itself perpendicular to the magnetic field. And it has small negative magnetic susceptibility. And the configuration has paired electron. Alright. So now when we come to hydrogen, we find that the hydrogen has got paired electron over here. Now since it has got paired electron, so it falls into this category. So hydrogen would be diamagnetic. And if it is diamagnetic, then it would align itself perpendicular to the magnetic. If I take hydrogen gas in a vial and place it in magnetic field, the vial would align itself perpendicular to the magnetic field. It would have small negative magnetic susceptibility. All right. So this is what molecular orbital talks about. Then we also have configuration. Now in this case, since there's a pair of electron in sigma 1s orbital, sigma 1s molecular orbital, so the configuration would be sigma 1s2. All right. An initial configuration for single atom of hydrogen was 1s1 and 1s1. All right. Let's try and understand configuration of nitrogen. Now if we take atomic orbitals of nitrogen, the configuration is 1s2, 2s2, 2p3. That is 1s2, 2s2 and 2p3. Similarly, if here also atomic orbitals, it's the same thing. 1s2, 2s2 and 2p3. So these are the configurations of atomic orbitals of nitrogen. Alright, so atoms of nitrogen. Now these two atoms come together and forms molecular orbital. S, as we saw in case of hydrogen, splits up into sigma 1s, sigma antibonding 1s. Then 2s also splits up in the same fashion, sigma 2s and sigma antibonding 2s. Whereas 3p orbitals, that is px, py, pz, px, py, pz, splits up into pi 2px, pi 2py and sigma 2pz as bonding orbitals. This we have got to keep in mind. And in case of antibonding, it forms pi antibonding 2px and pi antibonding 2py and sigma antibonding 2pz. So what we have got to keep in mind is, in case of nitrogen, not only in case of nitrogen, but also in case of BCN, the molecular orbital would be like this. The arrangement of molecular orbitals would be like this in case of boron, carbon and nitrogen. Alright. So we got these orbitals. Now we have got to fill up electrons. So first what we do is we count number of electrons. 7 from here, 7 from here. So we have got to fill in 14 electrons in these molecular orbitals. So we start with sigma 1s, we fill into sigma antibonding 1s, we again fill into, so 4 electrons supplied. Then again 4 electrons goes into sigma 2s and sigma antibonding 2s. So 8 electrons gone. So what we are left with is 6 electrons. Now 6 electrons, 4 electrons goes into pi 2px and pi 2py. Alright. And 2 more electrons left. They get into sigma 2pz molecular orbital. So basically what's the configuration? The configuration is sigma 1s2. We just are going this way, right? Sigma 1s2, sigma 1s2, sigma antibonding 1s2, sigma antibonding 1s2, and then sigma 2s2, then sigma 2s2, sigma antibonding 2s2, sigma antibonding 2s2, and then we go to pi 2px2, pi 2px2, then again pi 2py2, pi 2py2, and ultimately sigma 2pz2, sigma 2pz2. So these are all bonding orbitals. Alright, let's find out bond order now. Now as per here it says it has got 10 bonding electrons. So let's check it out. This is 2, this is 2, and again these two, so it comes to 8, and plus 2, 10. So we have got 10 bonding electrons. Now let's check out antibonding. It says 4. So we have got 2 antibonding here, then again we have got 2 antibonding here, so that comes to 4. So 10 minus 4 upon 2 comes to 3. 6 upon 2 comes to 3. So diatomic nitrogen has 3 covalent bonds in between 2 atoms. Alright, so that's about bond order. Now in case of magnetic behavior, it is diamagnetic. Why? Diamagnetic because all the electrons are paired over here. Alright, so what we had seen in hydrogen, also it was diamagnetic. Alright, let's understand molecular orbital for oxygen. Now oxygen, the electronic configuration for oxygen is 1s2, 2s2, 2p4. So we have got 2 atomic orbitals. This is 1 and this is 1. So 2 atomic orbitals of oxygen, which forms molecular orbital as explained earlier. Now 1s2, 1s bifurcates into sigma and sigma antibonding. 2s also bifurcates into sigma antibonding, and p orbitals, that is px, py, pz, px, py, pz mixes and forms sigma 2pz, sigma 2pz orbital, and at the top sigma antibonding 2pz molecular orbital, whereas px and py forms pi 2px and pi 2py, and pi antibonding 2px and pi antibonding 2py. So here what we observe is the difference is, in case of BCN, this sigma 2pz takes this position. Alright, so energy wise sigma 2pz in case of BCN is higher than pi 2px and pi 2py. That's the only difference which we have got to keep in mind whenever we are drawing molecular orbital diagram for boron, carbon and nitrogen. Alright. Now we have got to fill in electron. Total number of electrons, we have got 4 plus 4, 8, plus that 8 plus that 8 comes to 16. So we have got to fill in 16 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. When we are filling up electron in these orbitals, Hund's rule is obeyed. Why? Because both pi antibonding 2px and pi antibonding py orbitals have same energy. So whenever it has same energy, Hund's rule is being followed. Alright, so this is what is the configuration. And let us understand the configuration here. So same thing I have written over here. Now this becomes the configuration of molecular orbital. Alright, so this is this is this, Then comes this, which is this. Then comes sigma antibonding to S2, that is this. 2, these are the electrons, these are the electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. These which are superscript, they belong to number of electrons. Alright, so that ways, so carrying forward, then we have sigma 2pz2, 2. So we come to sigma 2pz2, then comes pi 2px2 and pi 2py2. So then comes pi 2px2, pi 2py2, and then ultimately it comes to pi antibonding px1 and pi antibonding 2py. So that is pi antibonding 2px1 since 1 electron and pi antibonding 2py1 1 electron. I have marked arrow over here just to make you aware that ultimately we are ending up with unpaired electrons. So when it is unpaired electron, that itself means it is paramagnetic. Alright, so it's paramagnetic. Alright, now let's understand the bond order. Now in case of bond order, we know it is Nb is equal to bonding, number of bonding electron is 10 and number of antibonding electron is 6. If we find out from here, we will see that we have got 10 bonding electrons and 6 antibonding electrons. So bond order is 10 minus 6 upon 2, which is 2. So diatomic oxygen has 2 bonds in between atomic oxygens. This is all about molecular orbital theory, MOT.